So thank you, Ambika, for a rather elaborate introduction, but that's nice. So while I have been largely working with graduate students and researchers, I love talking to students, and for the last 10 years, and that's largely because I wanted to convey the excitement of what is happening in the field of cosmology and gravitation. Okay, these are rather exotic areas. They don't really correspond to what you do in day-to-day life. There are many areas of physics and sciences in broadly which you can relate to, like diseases, and say climate and all kinds of things. This is not something that's very accessible. But what amazes me, if you have read the abstract, is the amount of understanding that we have been able to get about, who we are and where are we in our universe in the last, say, century, is mind blowing, right? It's something that one should pay attention to, because this, to me, is almost like a transformation happening. We are really in a situation where, as a species, we are sitting on this tiny planet and we are drawing fairly robust conclusions about how the universe began, how did it grow, how, how come we have a Earth and solar system around it. So let me begin with this beautiful picture, which is taken at the high altitude observatory. I don't know how many of you know, we have a high altitude observatory in Hanle, in Leh, Ladakh. And there's a 2-meter telescope, and the person who really runs the show there, Dorje Anchuk, is also a great astrophotographer. And this is the picture of the Milky Way, Akash Ganga. And, this sort of tells you, the splendor of the cosmos. So I wanted to start with that. And then tell you why one wants to do cosmology. And it's not that we want to do cosmology now. I believe even the prehistoric people in the caves, they had a better glimpse of the Milky Way than, I'm sure, than people who are in the cities now. I would have wondered, what's all this? Where are we, right? And so you can see this again splendid picture of the Milky Way reflected on a lake. It's a spectacular picture. The Milky Way actually is not, is just a part of the cosmos. We realized this again about a century back. There was a lot of debates. Is the Milky Way everything or not? And the way you can see it's not is these are largely stars and dust in between in our galaxy. So it's a plane which is obscured by our own galaxy. We are sitting in it. So you have to look away from that plane. So let's do that. We look away at a dark enough patch where we don't see any of our bright stars. Okay, and that's what Hubble did, and that's what was the latest telescope, big telescope, James Webb. So this is James Webb's deep field image. So about few years back, I used to show Hubble's ultra deep field. This is even deeper. And this is the tiny patch in the sky. I mean, this is exaggerated size on the, and you can see it's full of galaxies, right? It's like, a whole new, actually, literally a universe opening up. And you can see galaxies of all kinds, right? This is a foreground star, but you can see galaxies of various shapes. I don't know how many of you can see it very clearly. And, sizes. And you look at this little blotch far away, they look like just, very ill-formed galaxies. Galaxies, as many of you would have seen pictures, are nice spirals and elliptical. They seem to be, really not formed properly. And actually, that's the truth. These are galaxies so far away that they're just beginning to form. And we sitting here, are able to, look at these galaxies as they are forming, okay? And So let me sort of, before I jump into cosmology, talk about a galaxy. Okay, this is just to sort of try and get you to the scales that we are talking about, right? And as I told you, these subjects are not something that you deal with daily. So to us, cosmologists like me and many others, a galaxy is just like an air molecule in this room. If I want to really probe the flow of air, I don't worry about the structure of the molecules, right? All I worry about is how the molecule is moving. Or, if it's the temperature, then how is the temperature gradient moving, right? Similarly, in the cosmology that I'll be talking about, we are talking about scales so large that a galaxy on which, researchers spend their entire lifetimes working. So this is a completely, rich area of science, is something which is mammoth sized. Light takes 300 light, years to get across a galaxy. Okay, so 3,000 years. Sorry, and here you have a galaxy has 100 billion stars. So if our sun is quite an average star. So even if you take them to be that, so this is the mass of the galaxy. Now you ask, sort of what's the mass of the sun? Okay, I don't know whether you know this exponent system. It is 2 followed by 30 zeros and then a kilogram, right? So it's a mammoth thing. A star likes the sun. But, if I was talking about stars, then sun is really a, dwarf amongst many others. So if you look at the Orion belt, all the 3 stars in the belt are huge compared to the sun. Sun likes like a tiny thing, okay? So we are, looking at huge structures, huge distances. So when I talked about this parsec is about 3.26 light years. Okay, so to cover a parsec, you need 3.25 year. And so you're measuring, as I said, in parsecs. So I'll use that often, but I know you can just translate. This is a picture of the Andromeda galaxy. Okay, this is probably very close, to what our galaxy looks like, but Andromeda is bigger. It's the closest galaxy, and it's a sort of a spiral galaxy. Now we can't take a picture of our own galaxy, right? I mean, no one can go that far. But we have been able to map out our local region, right? So this is a satellite that is measuring the location of stars in the galaxy called Gaia. And so this is a smoothed out version of where there is matter around us. Okay, so the sun sits in a local kind of a void. There's nothing really immediate to it. And there are these rich structures around, and I won't really get into that. All I wanted to point out is this is, about 2,000 light years to the edge of the picture that I'm showing you. Okay. Now, up to this part, there is one other aspect of our place in the universe that is being studied, which is, you want to know where you are, and the other question many of us ask, are we alone? And this is roughly the distance, and you see 2,000 light years is not much compared to the size of our galaxy. So only in a patch of a galaxy, we have been able to search for other planetary systems and look for this. That's again a rich area that is growing rapidly. Exoplanets is the word. As of May 16th, this I picked up from Wikipedia, there are these many confirmed exoplanets. There are these many solar systems, solar-like systems. These planets are in systems, and 950 of these systems have more than one planet, right? Now imagine we are looking at only a little volume of the galaxy and seeing so many exoplanets. Imagine how many planets are there in the galaxy. And then if you remember the picture I showed you from James Webb, there are billions of galaxies. So, if you are a logical person, you would think it's very unlikely that life didn't take root in any other place in the universe. Okay? And these are just some classifications. And what I wanted to also show you how rapidly a field grows, right? So this was the situation when I was, let me read this. Yeah, this is almost like my research career. There's hardly any talk about exoplanets then, and now this is a thriving area, okay? But let me now move to bigger scales. Now I was talking about area around us which is 2000 light years in radius. Now I'm talking about an area which is 100 million light years. Okay, this is getting to scales where obviously it takes 100 million years to cross, but we have been able to map out the structures there. The very big, what you see as a point is actually a whole collection of galaxies. These are clusters of galaxies, and there are these local ones, then there are big ones, Coma cluster, Virgo cluster, and this is the nearest big cluster we have. And you see that matter is distributed in an interesting pattern around us. Pattern in the sense it's not a set pattern, it's a random pattern, but it's not uniform, right? Then you again make a zoom out and you see this 100 million light years is now this part, this scale. So we're looking at much bigger scale here. And these clouds that you're seeing are these superstructures of galaxies and things. Okay. I should also tell you, please feel free to interrupt and ask questions. Okay. And so this is the cosmic arena. But yeah.
Sir, in the previous slide, you showed that the dots were representing galaxy clusters.
Hmm.
Sir, and in the whole picture, sir, in the slide you switched to galaxy clusters. So in the whole picture, there are only a limited number of dots representing galaxy clusters.
Yeah.
So are there any galaxies in between, in the empty spaces between these?
No, so these are largely field galaxies are not, represented here at all. So we have looked at what are the largest things. So this one probably is one of those cloudy structures here. So here they chose to represent it as points, and it's only local. So you don't see that many of them as you see in the next picture. Okay, and in the next picture, I'm sort of trying to take you on a ride through the cosmos. So this is, of course,
So you showed just now because of the cosmic web or
yes,
cosmic supercluster.
it's the cosmic web, yes. Uh, and so this, I'll take you on a ride through the cosmic web. This is a video which tells you if you were in some magical thing where you could, Star Trek kind of a thing. This is what you'll see as you zoom in, right? You'll see clusters of galaxies and, structures all around. So this is, again, the point to remember, it's not uniform. They are very well formed structures. And as she pointed out, reminded me of this. This is called the cosmic web. Okay, so that's very nice. Okay, so you see this amazing thing that we need to understand. It's quite complex. Oh, I'm sorry, I didn't notice. Cosmic web is, if I look at the distribution of galaxies, they seem to be, distributed in a very cellular structure, like a sponge or something like that, right? So it's not a uniform, flat, distribution. Okay.
Some you mentioned about the discovery of exoplanets. So in the exoplanets graph which you showed, there was a boost in the discovery of exoplanets in like around 2016. But then it came really down. So what was the reason for that?
Okay, I wouldn't exactly be able to tell you, but there was a dedicated mission, I think called TESS. So it started detecting, or Kepler maybe. Kepler was one of the missions dedicated to detecting exoplanets must have taken off. Yeah.
Excuse me.
Yeah.
So in the last slide, there was a cluster of, so there were like clouds and all. So how was this graphed? We would know some parts that we see from Earth, but how was this actually graphed, and how do we know that these superclusters exist?
Oh, no. So these are actually, the galaxies are seen,
Yeah.
and then you can also estimate their distance, which I'll mention how.
Okay.
through something called redshift.
Okay.
So you can place them in 3D pictures. Okay.
Okay. Thank you.
So my question was, sir, in the image that you had shown about masses, sir, about the mass distribution in the
You're right.
universe. So I remember that there was a big gap or a big hole that
Oh, that was
in the
right
bottom
in
right.
our
Yep.
local neighborhood.
No, sir, in the bottom right, if you see, there is a very big void. Is
This
there
one,
any
right? Local bubble.
bottom right? Bottom
Oh,
right.
here.
Yep. Sir, is there any
Yeah.
reason for
So
that?
there are such things, but this is on scales of 2000 light years.
Sir, okay.
What I'm worried about is how is it distributed on scales of, 100 million light years.
Okay, sir.
Okay. So now I'll skip this, and this is kind of the distribution. Now you can see this is a light, this tick represents a billion light years, right? So, and we have mapped out galaxies on such volumes. Okay, it looks like a story, but and we are somewhere here. The Virgo cluster I mentioned is right next to us. It looks like a cousin. And so the question is, if I were to start cosmology now with all the observations, how would I deal with cosmology, right? And the way we will, we do is in physics. I mean, you're all ninth grade, so you'll get into physics. You notice in physics, what physicists do is try to look for an appropriate approximation. Like if you're looking at a ball rolling down an inclined plane or something sliding down, you may set friction to 0 if it's a nice plane, and that gives you a fairly good answer, but it makes the problem easy. Similarly, whenever you're faced with such thorny problems on huge scales and structures, in physics, we take a appropriate approximation. Okay, so you want to speak in the mic or? Okay, fine.
Sir, when you talk about the galaxy's mass, then I had a question: how is the galaxy's mass measured? So does that mass include only the stars or the planets as well? And what is supposed to be?
Yes, so you measure in various ways. One is, you measure the number of stars and local, the density. So these are not exact measurements that, there are, so many galaxies, but rough estimate of that can come from that. Or you have other dynamical measures of how much is this mass affecting, how much of the light is emitted from that, and you convert the luminosity of stars. So you assume they are, the simplest thing is to assume they are all shining like the sun. And then you can multiply that and then see how many suns are needed to explain the luminosity.
So are the planets' mass measured as well, or just the stars?
Oh, no. At those scales, we can't see planets. We cannot see planets outside our own galaxy, let alone that. I mean, we can see it only in a very local region of, 2000 light years. 2000 light years at least we can, in a science fiction way, think of sending a ship with people in hibernation or something. I don't know. I mean, and get to the edge. But beyond that, I'm not sure, you will be able to connect back when you come. Sorry, you're okay?
Mic, okay. I've heard that at the center of every galaxy there's a supermassive black hole. So how do we figure that out? Because
Okay.
black holes don't emit light; they absorb all the light. So how can we see an object without light?
Okay, so there are two answers. Till a few years back, we would have basically said that we infer it, because if you look at stars, okay, so in the galaxy, the stars are not sitting idle. They are actually, sun is rotating around the galaxy at 220 kilometers per second. Okay, so I don't know whether you realize when the earth is going around, revolving around the sun, it's actually at 30 kilometers per second. It's a fairly large velocity, right? So I hope no one starts feeling sick. We are on a, a fast-moving thing, and then the entire solar system is revolving around the center of the galaxy at 220. So that allows you to use Kepler's law to estimate how much mass must be enclosed. Okay, And then when you go towards the center of the galaxy, you see stars rotating very rapidly. And we have been able to map out the entire orbits and then infer that there was a bright spot in our galaxy, in the X-ray spot, which was called Cygnus X1, okay, and X something, okay. And so the Cygnus is now known to be a supermassive black hole, not only because of dynamics, but of the fantastic picture which was on the front page of everything. The Event Horizon Telescope actually mapped for you the radiation from matter around the black hole. Now, if there are black holes which don't have any matter, they've eaten up whatever is available, those you will detect through another new area of observational cosmology that has come up, which is gravitational waves, right? So these black holes, when they merge, they emit gravitational waves. When things fall into a supermassive black hole, they emit gravitational waves. We haven't gotten to that, but a decade later, there will be something called laser interferometer space antenna, which ESA is going to launch. I mean, it's already a completely approved project. And that will see things falling into a supermassive black hole and infer the entire space-time around those supermassive black holes. There was a hand up. Oh, we are, sorry. You should keep a mic with you.
Yeah, sir, I just had a question that
Yeah.
as he said that how can we figure out that there's a black hole in the middle of the galaxy? So I'm just saying that can we figure it out through the event horizon of the black hole?
Yeah, we
Matlab-
can't see the event horizon readily, right? So what you can see is something which is a little bigger than the event horizon, where matter is still swirling around. And there is something, there's an orbit around which lights, you get a light ring. Okay, and that's the thing which is a sure shot signature of a black hole. Okay. No, so we will have less of discussion time, right? You said 45 plus 45. So I think let it flow. Yeah. Unless you have a different. Okay, great. Yeah.
I had a question that most of the matter in our universe is said to be made up of dark matter, correct? But there are many studies which say that they do not exist, or like there are many generals which say that. So do they exist or do they not exist?
Okay, so dark matter is the explanation for what we see in cosmology till now. It's the most economical and most robust way of understanding, which doesn't necessarily, in science, one thing you should realize is nothing is engraved in stone. At this point, the best understanding is that there is dark matter. There is another kind of matter which clusters under gravity, but does not interact with light. Okay, we haven't seen any particle like that. It could be small black holes. It could be many things, or it could be a completely different theory of gravitation on large scales. Now, at least I don't see a convincing, alternative yet, which doesn't require dark matter. Okay, so let me proceed. Oh, okay.
So my question was that, could you explain about the shape of a black hole? Is it spherical or like?
Black holes are always spherical in 3 dimensions. You may have seen complicated black holes, but they exist in the realm of people who work on high energy physics involving a lot of other dimensions. But black holes in the known 3 and 1 time direct are spherical.
Thank you.
So as Ambika says, maybe I'll take a couple of questions and then move a little ahead.
Sir, my doubt was that how do we calculate distances in the curved space-time?
Yes, I'll get to that. Yes.
I have a question. Is as the universe is expanding, is there a possible time where all the like
It's coming.
galaxies are so far away,
You're,
we are
you're
unable to see
almost
them.
telling me what to talk about. It's all there. Just wait a few minutes, we'll get there.
Sir, if time is relative and matter falling into black holes takes longer to fall in, so does it actually ever fall into the black hole or does it just stay at the event horizon?
You don't see it fall, but it does fall into the black hole. Okay, so great. So we will move a bit and then we will take another round of questions. So let's look at this box. This is a typical sample. Like if you have a condensed matter uh, experiment and you see some weird structure, or you have a biology petri dish with weird structure, you take a little sample and look at it, right? People do that to your body also. They do biopsy. So if we do a biopsy of this, this is what you get. Okay, this is actual data from some survey of galaxies done quite a couple of decades back now, called 2-degree field. But you can see that in about 326 million light year box, which is basically 100 parsec, million parsec, megaparsec box, this is how galaxies are distributed. And the gray thing is something just to highlight that it is got a cellular structure, right? It's not a uniform distribution of galaxies. Now, if I were to now understand how did this whole thing come about, right? This must be something around us also, right? So this is a typical volume of the universe. You can pick any volume there. It looks like this, not in exact where, detail, but statistically the same. So now comes the whole fun of physics. Okay, now how do you simplify this problem so that it's tractable? Okay, so when Einstein and all others sort of first models of cosmology were proposed, that's more than a decade, century back, they said, oh, let's take a homogeneous distribution of matter, which now we know is not great, right? But it's not a bad approximation. And it was clear even in the 70s, what you do is now you don't worry about the three-dimensional distribution of galaxies, but look at the sky and project it back. Okay, now this is from something called the Lick survey, observatory survey, and this is the northern hemisphere, this is the southern hemisphere, galactic, and then you can see a part which is missing. Does anyone know why a part would be missing in those days? Can anyone? No. Yes, so we are sitting in our galaxy and the galaxy has a lot of dust, so optical surveys cannot see through that. Now we have a lot of infrared observatories which now we can have much more reliable full sky. But what you can see is no direction the sky was crying out for attention. It's not as if there were lots of galaxies here and very few galaxies in a, it is kind of, rough, but the roughness is the same all over the sky, right? That if you take as a statistical thing, that I look at every part of the sky, average the mass, you will have the same amount of mass, okay? That means the distribution of matter is isotropic around us, okay? Now comes a leap of faith, okay? It's a leap of faith, so we may be wrong here, but you assume that whatever physics operates here, operates everywhere. Whatever we are seeing, we cannot be in a special location of the universe. This is, I would say a super Copernican principle, right? I mean, Copernicus told us don't think that everything is revolving around the Earth, and we have a heliocentric model. And similarly, you shouldn't really think our galaxy is special. There's no reason for it to be special, okay? If you assume that any observer anywhere in any distant galaxy will see a uniform distribution of mass, then a simple maths theorem tells you that the distribution has to be on the average homogeneous, okay? So which connects the loop back to something which was proposed 50 years back. So this is in the 70s. You can observationally say, okay, old Einstein was right. I mean, a homogeneous thing is a good model. And that takes us back to the early models called Friedman, Lemaitre, Robertson-Walker models. The name is unimportant, but this is the background model which is a very good approximation to how the overall universe is evolving. Okay? And that comes by, so what you do is now take a homogeneous distribution of matter, and you can't use Newtonian gravitation anymore. You know that Einstein's gravitation is this, general relativity is the story. So this is one of the simplest problems that you can solve. You solve the equations of general relativity for a homogeneous distribution of matter, and what you get surprised everyone, right? What you find is the space is no longer static. We always assumed, space is a static arena, right? I don't expect anything funny to happen, the room squeezing or expanding or anything. But the universe seems to be expanding in time, right? So you have solutions only that expand in time or contract in time. And you see, there are very interesting effects of that, and cosmology at one level is just doing normal room, not room, but terrestrial scale laboratory physics applied to an expanding arena. That's all. Every effect that you see which are cosmological is because the arena itself is expanding. So this is a lattice of galaxies, just to point out that what's happening is not as if there was an explosion and things come out from one point, which some of the BBC serials do, like there's a rumble and something. So there's not an explosion. Every part of space is expanding in time, and it's happening the same way everywhere. Okay, so this is a better picture to have in mind, and interesting things happen there. If you see the shell of light, you can see the light shell is kind of struggling against the expansion, and the expansion, there's no limit on how fast you can expand. So it can be so fast that the shell actually is not moving at all, right? It gets stuck, okay, and such things can happen. So let's look at the observation part. So this was some theoretical model which said space is expanding in time. Even Einstein didn't believe it. He tried hard to get a static model of the universe, which was a very unstable model. But Hubble, who was an observational cosmologist, looked at galaxies close by, and he noticed that galaxies seem to be receding away from us at a velocity proportional to the distance. The further they were, the more was the velocity. Now, if you go back to this picture, this is exactly what is happening. You see the first ring of particles around me will be going at some velocity. If you are looking at a distant ring, it will be going proportionately faster away, velocity, apparent velocity of precision. Okay, I'll get to your question. Okay, so now that expansion rate is somewhere around 70 kilometers per second over a megaparsec. That's unimportant. What is important is the model of cosmology we have is so simple that also tells you the characteristic density of the universe. Okay, now any system that you study, you want to gas system, you want to know what is the density, right? I mean, the first thing you want to know is, is it a dense, medium, light? So the cosmic density, if you are interested, is 10 to the minus 29 grams per centimeter cube. Okay, so this is now 30 zeros and 29 zeros and then a 1. Okay, and this is how brave Hubble was. He measured the velocity of galaxies close by at distance of few megaparsecs. He had this scatter of points and boldly fit a straight line through it and said, look, an expanding universe. It turned out to be right. Okay, so that's another thing I wanted to tell you. A lot of scientific breakthroughs are, bold ideas. You cannot, hold back. You say, okay, this looks like this. Time will tell whether it's right or not. So that time did tell. So now this is a recent measurement. Now, if you remember, this goes to 2 megaparsec. This straight line goes to 200 megaparsecs, 400 megaparsecs. To 200 times more distance, we see the same law. Okay, and this law is completely explained by that picture I showed you of a expanding membrane. So space is like a membrane which is magically expanding in time. Yes.
So I was just confused that there's a expansion method to calculate, like it's the Hubble, we already
Sorry. Can you?
Yeah. There's, I think, a method to calculate the expansion of the universe. So I guess it's purely Hubble expansion method or something. So, sir, I just wanted to ask that the Hubble constant's value is always changing. So, sir, I'm not
Yeah, so
sure
what we talk about when I
what's
say
the
there's a H naught here, this is our cosmologist way of saying it is the expansion rate now.
oh, okay.
So this is the straight line, it seems to be working fine. It basically tells you that if I look at the spectrum of light coming from a distant galaxy, because it's receding, apparently receding fast, the spectrum will be redshifted, Doppler shifted, right? So you can use actually the spectrum of light from a galaxy to estimate how far it is, which is where, going back to the question of how we made the 3D map, is from these redshift measurements. We can look at spectrum and see that the spectrum is shifted, and you estimate the redshift, and you can immediately translate it to distance. So there's a linear relation which you can use. And you can now start building a story of a space-time. Okay. Oh, this is interesting. I've never seen this before. Get the mic, actually.
Most people believe that the universe started with the Big Bang, right? It started at an infinitesimally small point. But why do we measure the distance of galaxies when we're calculating Hubble's constant? Why do we measure it as the distance from Earth rather than the point at which the universe began? Because
no, so there's no special point from which it began.
But it began at an infinitesimally small point,
so that's,
right?
okay. So let's, let me tell you. So we are right at the picture where you're talking. So this is a time section. Okay, there's an assumption that all clocks in the universe work the same way because atoms are the same everywhere. Okay, now you look at this section, these are galaxies. Okay, they are receding away. So this is space and this is time. And you can see that this is a nice way to depict Hubble expansion around this galaxy. But if I were to take this galaxy, I will see the same picture, right? Now, as you see, the lines are converging, okay? Now, mathematically, I mean, see, we do cosmology by looking back, right? So we know cosmology up to a few fractions of a second very well. Beyond that, we don't know what happened. But if you look at if you're a mathematical GR person, that space-time extrapolated back will have that infinite density. But in physics, we don't have infinite densities. We don't like such things, infinities, right? So we believe it will be cured by some quantum effects because you will get to energies where quantum gravity will be important, and that will cure it, is our belief. So it's an extrapolation, and you should see that what's amazing is the universe is 14 billion years old, okay? And we can tell you how the universe was when it was only 10 to the minus 16 seconds from this extrapolated Big Bang. So Big Bang is the extrapolated point, okay, meeting point. Yes?
I wanted to ask about that means, sir, if galaxies are... So my question was, if theoretically a galaxy is far enough such that its recession is faster than the speed of light coming from the galaxy, does that mean there are some galaxies that we will never be able to see?
No, that because light, you're saying the velocity will be greater than velocity of light.
Yeah.
Okay, I don't want to spend too much time on it, but you see, these things are called light cones. Normally, in special relativity, the light cone is upright. You can see these light cones are tilted.
Yes.
So a galaxy which is appearing to move at some velocity is actually not moving at all in its light cone. It's, it's at the center of the light cone. So this galaxy is not really moving relative to the local space. It's an apparent movement, and I'll tell you why. The Doppler shift is not real Doppler shift as we think. It's a very approximate way of looking at it. Okay, now what we can do is this space-time diagram is not easy to work with because this is how light travels there, but we do special relativity where light travels on 45-degree lines. We want to get back to that. I know none of you would have done special relativity, but that's okay. So what we do is divide out the expansion at every step of time. I divide out the spatial distances by expansion. So instead of this, jhadu kind of a thing, you get these straight lines, and that tells you that there is no center to the expansion, right? There's no point at which you can say it converges. And then every time slice, now you can see that spacing between what was equal time has changed. It is getting shorter. But the nice thing is light travels on 45-degree lines, okay? And from this picture itself, you will get to understand one of the absolute pillars on which cosmology rests, which is translating redshifts to distances, okay? And it is not a Doppler shift, and I'd like to convince you of that. So when we talk about redshift, what are we looking at? We are looking at a red light, say, or blue light, okay? What is a blue light? It's a periodic, wave. So there is, troughs and crests coming at equal time. And you measure how much is the time period, you convert it into a frequency, right? So let's look at this piece of that space-time. Light travels at 45-degree lines. So let's say that this galaxy is sending out periodic signals, okay? So light comes here, and this is the observing galaxy. Now notice that this galaxy send out in one cosmic tick this light, right? But when I measure it, it's already 2 cosmic ticks. So the frequency will appear to be half, right? The time period is twice, so it will be half. And this is what you are seeing. You are not seeing actually a velocity shift, but just the fact that an expanding universe has these amazing things that normal physics in a static thing doesn't. And this is what you have to wrap your head around in this, okay? So you can see that it's very easy to understand why we can trade distance measurements for measurements of spectra and get distances, okay? So equal time events at a distant galaxy appear time dilated. So when cosmology came, the only example of time dilation we knew of was Doppler effect. So observers started talking about velocity, but that velocity is a pseudonym because the velocity can exceed light, speed of light, everything. I'll get to your question. Okay. So then frequency of light from a distant galaxy is scaled by the expansion. So there's a very simple relation between redshift and galaxy. So above redshift of 1, Z of 1, every galaxy that you see will have a redshift which indicates a velocity. If you interpret it as velocity, it will be greater than the speed of light, which obviously tells you that, but no physics changes in cosmology. So we know that nothing travels faster than light. Okay, there was a question. You were the one?
Yeah.
Okay.
So you said light travels at 45 degrees.
Hmm.
I'm not sure what that 45 degrees is to.
Okay.
What's the baseline for that?
Okay. So this is basically space, say measured in meters, and this is time, but again measured in meters. Yes, because the speed of light is a universal constant. I can always take time multiplied by the speed of light. So velocity is distance over time. Then I multiply with time, then it becomes a distance. So this is what Einstein told us, that time and space and time can be traded, and that's because the speed of light is a universal constant. Okay, this is something that you won't have to worry about for now. Okay, one of the, again, the consequences of an expanding universe is this. You look at a box, like I showed you this distribution of galaxies. So you look at a box and you see, of course, the box would be smaller in the past. So let's say it's half the size, quarter the size. the density of galaxies will grow by a factor of, when it's half the size, it will grow by a factor of 8, number density. When it's here, it will be 64. But now look at light. If you have a light in a cavity and the cavity shrinks, so number of photons, of course, scales like the number of galaxies. But remember, the light's wavelength has become half, which means frequency has doubled. And you know that in quantum science, quantum physics, we are told that frequency tells you the energy of the light. So the energy of the light actually goes by another factor of this expansion, fourth fraction of the universe. So the upshot of this is, if I have, at this point, the density of light is kind of 1 over 10,000 of the, mc square of the mass that you see in the universe. Okay? But in the past, since the density of light, radiation is growing faster, there's a time when the universe was 10,000 times smaller than now, when the universe becomes equal density in matter and radiation, and prior to that, you can forget about the matter. It's only radiation dominated. So the early universe is radiation dominated, right? Now that's even simpler. I don't have to worry about all these galaxies to understand how the universe behaved in the early universe times. So you can actually map expansion history and do all that. So let me skip over that. And you can actually go back and use the basic physics to understand the universe that you see now and the universe that must have been in the past, okay, theoretically, and then try to match it to observations. Okay, this is the whole game of cosmology. Now, one of the things that played a big role, which Ambika mentioned, is the cosmic microwave background. Now, if the universe was all radiation, where is all the radiation, right? And we discovered it by chance in 1965 as a uniform radiation, that glow that seemed to be coming from every direction in the sky. And if you really computed the energy density of that, it accounts for 99% of the radiation density. X-ray background, gamma ray background are minuscule compared to that. Okay, I'll get to the questions. I can see your hands. Okay, so this, when we measured in 1965 and onwards till 1992, looked uniform all across. Okay, in fact, this is uniform at the level of 10 parts per million, which is a much stronger case to say that old Einstein and his other researchers of that time were very right. The universe is actually very homogeneous and isotropic in the past. So we did start with a completely homogeneous universe, an isotropic universe. Okay? So I will skip this since, so now I'll take the questions. There were 2 questions. No, not, there were hands there. Yeah, right. I'll take 4 questions, don't worry.
Do you believe that the universe started with the Big Bang, especially considering the fact that there have been multiple theories against it? Also, taking in the fact that the right amount of lithium that was produced has not been found. Also, do you believe that we will ever be sure that the universe started with the Big Bang?
So that's what I said. The Big Bang is a mathematical extrapolation. So we expect that the initial period of the universe will be different from what we are saying now. And we have good guesses for that. We don't know what it is. Now, there are very different models of cosmology which don't predict a Big Bang, but those are not consistent with observations at this time. Yes?
As you said that universe is expanding in interval of time.
You can talk.
Interval of time period. So, what do you think that impacts will we have in upcoming years when the universe would be expanding? Like, what all differences would we see?
very little, because the expansion rate is such that, you know, you will see differences, you know, on billion years time scale. On the other hand, there are people who are already computing how the distribution of radiation will look like, and I'll get to that, what I mean. In 100 years time, we could potentially have, you know, assuming that even instruments get better, people have tried to look at that, but I mean, look at this possibility.
So we know that universe is getting affected by, the expansion of the universe is affecting the light. So are there some solutions so that the light isn't very much altered by the expanding universe? Because it may affect, you know, the planets.
No, so that's the thing. So other thing which I should tell you, and this was one of my questions when I started research, was if the universe is expanding anywhere, how do we measure the expansion? Because my stick is also expanding. But the thing is, whatever is gravitationally bound, like our solar system, does not expand with the expansion of the universe. Okay, unless the expansion is extremely strong, but normally it wouldn't. A galaxy doesn't, a cluster of galaxy doesn't, a supercluster mildly feels the expansion. So the expansion is felt at very large scales, and it doesn't affect anything that we have now. So it's negligible on your time scales as well as your scales of measurement. And also, if you are stuck in the solar system, you won't see it. But cosmologically, there are signals which will change, and they change on millions and billions of years. But now we are so confident about things that we are trying to see if 100 years we can see, you know, 10 to the minus 7 effect. Yes.
I have two questions. One question is, if the sun dies, which would we feel like first? The gravitational force not acting and we drift off, or the light won't reach to us, like because it takes 8.2 minutes.
Oh, no. So gravitational effects and light travel at the same speed. But the way the sun will die is it will first expand and burn up all the, you know, planets, including Earth. It will swallow everything. Okay, it becomes a red giant, and then it will collapse. And all this, if you're seeing from outside the solar system, all the signals will travel at the speed of light, right?
And my second question is, suppose you leave an apple inside a container for billions of years, and because energy cannot be created nor can it be destroyed. But sorry about the change in topic, but what would you think could happen if you opened that container if no energy was lost and
again, you have
left
to
the
talk
box?
about a container on cosmological scales. On our scales, no expansion is happening. But it's a very good question, and it brings back one of the issues with general relativity, that there are no global conservation laws in general relativity. Everything is a local conservation law. So you don't have a global conservation of energy. And I can't get into it further at your age, but you can talk to people and find out.
Thank you.
Catch Shomo Prize with it. Okay.
Sorry, this is a bit off the topic, but I read one of your articles, and the observation of gravitational waves from 22 solar mass binary black hole collisions. So I had this question is, can you elaborate on how the significance level greater than 5 sigma was determined for this event?
That's totally out, so we can take it in the discussion time we have. Okay. For now, please ask questions that go with the flow of the talk now. We'll take any other curiosity questions later.
Yeah, I had a question about the CMBR. You mentioned that the universe is constantly expanding, and And the radiation that we see from the Big Bang
So
is.
let's get to that again. I'll talk about what you look for. Okay. So at this point, till from 1960, this is the observational view of what we are seeing in the universe, right? So when I look out, I'm seeing galaxies few billion light years away, right? So there's a distribution of galaxies here, and we are lucky enough to peer all the way back to a plasma surface. So it's I can't get to the space-time diagram here because you guys have to grow up to that. But every observer in the universe seems to be surrounded by a plasma all around. It's all around us. So it's like a super IMAX theater because that plasma corresponds to a universe which was only 500,000 years old, whereas our universe is now 14 billion years, right? So that means we have a time machine. Cosmology is a time machine. Like he mentioned that sun, we will see 8 minutes back, right? So when I see a galaxy, I'm seeing it way back. I told you we are seeing galaxies as they are forming, right? Similarly, this is a very, very early glimpse of the universe. So it's like seeing a 1-day-year-old kid and the 100-year-old man, right? Something like that. So this is transparent, which is nature's gift, and we can see this. This is the cosmic microwave background. The glow is coming all over the sky. Now, of course, you don't want to sit in a super IMAX theater and see nothing, just a blank glowing screen. That was the situation with us for 25 years, till we started seeing fluctuations in it. So 75, this was discovered, and 65 it was discovered, 75, these are the Nobel Prizes corresponding to the discovery of the black, cosmic microwave background. This is the first fluctuations, and then the understanding of the cosmological model. So this are now slightly hotter and colder spots at the level of 10 parts per million. Okay, now it's fun. Now I can see precursors of the fluctuations that could have given rise to the galaxies that we see. Right? The galaxies are no longer uniform, but if you have tiny perturbations in the early universe, we can explain how galaxies would form this structure. So we have a consistent picture connecting this to this. However, the picture of what created this fluctuation in the early, in this plasma at all, is still, awaited. We don't have a clear picture of that. Okay, so let me skip this and tell you that this field has been enormously successful. So it's, and amazingly again, it's completely aligned with my career. So 1990, I started my research. Kobe discovered the first fluctuations on this super IMAX theater in the 1990s. So this was a space mission from NASA, but it was at very poor resolution. It's like as if you're seeing without your glasses, right? If I take off my glasses, this is what will happen. Then the next decade, there was another mission from NASA called WMAP, which you can see now started resolving all those finer structures on the screen. And then the last decade was absolutely the most highest resolution map of this screen. So these are 3 landmark missions. However, there have been many other ground-based and balloon-borne experiments which contributed to this whole story. And this story was so successful that our knowledge of the universe from 1990 to now has grown by 1 billion folds. This is an estimate made on basis of how much uncertainty was there in our understanding of cosmological content and expansion rate and all. So that volume has collapsed by at least 1 billion fold or even 10 to the 14. So this is, about 3 times faster than Moore's law. Okay, how much we have been learning about the universe. So let me show you the showpiece. So this is the entire sky. Now astronomers plot the entire sky in these ovals. Okay, so this, imagine you can put it on a sphere. There are nice, there's actually, I didn't put a thing, there is a nice site where you can look at the sphere and play around with it, and you can look for funny shapes. But this is random fluctuation. It's like a sandpaper kind of a thing. Okay, it's the same everywhere, but it's not smooth. You see these roughnesses. Now, one way to measure roughness is something called root mean square, right? You look at these fluctuations, square those fluctuations and take a square root. That gives you a handle on what is the roughness of the sandpaper. So when you buy sandpapers, there are different grades, right? The boys may not know, but girls who do their nails would know that the sandpapers come in different things. I don't know how many people have you used sandpapers at all? Or is this something, this is a rough paper where you polish things. Okay. So the same analysis, so what you do is, this is called something called power spectrum. You look at fluctuations on different scales, right? And then that can, quantify this completely, this sky. So you look at something which is angular scale here. This is going to small angular scales and tells you how much power is there at different scales. The amazing thing is, in cosmology, we actually predict a very rich structure in this power spectrum. Given different cosmology, this power spectrum moves around, right? So now, depending on what you put for various values of the, how much ordinary matter is there, how much dark matter is there, how much dark energy is there, this curve will move around, okay? But what Planck provided you is a very accurate measurement of that over this whole thing, these green points. So the game in cosmology has been to move these dials around. I know any of you can sit and do that, 6 dials, and you can change it, and then find a set of values where the predicted curve exactly threads all these things. And we find that, and that's our inference about various things like how much ordinary dark matter, how much cold dark matter, how much whatever, expansion rate. So much so that, and I also wanted to tell you that this physics is very, very well understood. So it's laboratory physics. I don't know how many of you have done a resonant tube experiment. There's a tube and then water levels and you make it resonate with a tuning fork. No? Okay. If anyone who's doing science probably will get to that at some point. But it's like a resonance experiment. So I'm glad I didn't get into that. This is actually the measurements. You can see that these measurements have error bars which cannot be seen, right? These points have error bars which you can see by differencing the measurements with the red line. And now with this kind of a measurement, there's not much play in what kind of cosmology can work. Okay, so any cosmology, and going back to the question that came from, why do you believe this hot Big Bang, is that there's no alternative which fits this as well. Okay, so we are not saying we have the final model of cosmology, but there's a model which works. And if you look at the parameters, like how much of ordinary matter there is, like things, atoms that we are made up of, it only, we know that to 1% accuracy, expansion rate to 1.3. This is unprecedented in cosmology. Over the 3 decades, when I started, these numbers were not known very well at all. Okay, so we have a standard model and we know what the cosmic content is. So you see the pie chart here. What we know of in terms of atoms and all the particle physics experiments and everything only accounts for 5% of the energy density of the universe. Okay, another 25% is something we dub dark matter. It could be something else, but it has to be something that clusters under gravity and cannot have electromagnetic interaction. And if that was the surprise till the 90s, we thought, oh, we have to deal with dark matter. Then at the end of 90s, we realized, no, so this only accounts for 30% of the energy density of the universe. The rest, 70%, is made up of dark energy. And the cosmologists have the trick. Anything we don't understand very well, you put a dark to it and then, we are done. But the dark also indicates that this energy density also cannot interact with light, because then we would see it. But we feel them, right, in our measurements. And if you look at this wedge, this is how it is, starlight is again a very small part of it. much of it is hot gas in the intergalactic medium and things like that. So it's a very rich field. So we have a very simple model we started with, right? And this is a message to everyone, like simple things are not necessarily boring, right? When you look at, oh, this is a simple formula, it may not be. Actually, all of the model can be, one algebraic equation. But we started with that, yet we inferred a very exotic universe. 95% of it is yet to be discovered, right? So the message I want to send to your generation is cosmology is just beginning. A lot of people go around saying, oh, cosmology is all done. We just have a model which works, okay? But we don't know any component of the model except for 5% of it, and that little bit of 1/10 to 4, like 1 in 10,000 of the radiation. That's all we know. So there is a part which is dark matter, which we cannot see directly through light, but we infer it through the gravitational effect. It affects the dynamics of galaxies, clusters, and also the cosmos and the CMB, the fluctuations. We also know the dark energy is some smooth form of energy. It doesn't have an effect on small scales, it has an effect on large scales, and it's sort of repulsive under gravity. Okay, so if you take dark energy, it doesn't want to cluster. And it's detected by its effect on cosmic acceleration, expansion. The expansion rate actually accelerates when the universe is dominated by dark energy, which it is now. So we find an accelerated. Also, it affects the growth of these structures. The structure growth is very different with and without dark energy component. And with the measurements we have, we can say that dark energy must exist because that's what explains the distribution of galaxies. But this is, of course, something that will keep going on. There are people in deep mines looking for dark matter particles, and that's a rich area, of things. Dark energy, there's an entire space mission called Euclid, which is mapping out galaxies so that they can see some hints of what the dark energy is. Okay, at this point, we believe it's something like a cosmological constant, which Einstein introduced and then said, oh, there was a big blunder. But it turns out to be not a blunder again. But another main thing, if you remember, go back to that picture I showed you. The success is we saw fluctuations in the radiations at 500,000 years old. We can connect it to the large-scale structure in distribution of galaxies now. But we don't know where the fluctuations originated from. And for that, we are completely convinced that it has to be some ultra-high energy physics, which we have not discovered yet. So even for people who want to get into high energy physics, that's again something that is there. And it may be signs of some new fundamental physics which we don't know, which will unify all interactions maybe or something like that. Okay, there are other bigger questions you can ask with the kind of observations. You can ask if the universe is infinite. You can have a universe which is flat, but wrapped as if it's a cycle tube, like a torus. You can have more complicated shapes. You wouldn't know unless some observations show up. And there are people who are looking for such exotic signatures also. You can have slight bit of rotation of the universe. We are putting limits on that, but there's always limits. But going back to this question of what created the fluctuations, as I said, all the success is from this screen that we are seeing and these structures and connecting that through the evolution of these fluctuations to this. But what gave rise to the fluctuations themselves, we have only a very good guess. And the guess is quite interesting. If it is right, then everything we see in the universe arose out of quantum fluctuations. Okay, and we know how to work it out in theory, but we need to see all the signatures of it. Till now, everything is consistent with that, but there is one thing that would really nail it, which is to see gravitational waves from the very beginning of the universe, from that stage. Okay? And we are looking for that. And there are lots of efforts going on. So I just wanted to, so this is something that we will do in the next couple of decades. We are all working towards it. And in India, we have a collaboration which is, proposed that ISRO takes part in this mission to map this same day sky accurately. It will be seen in the same day sky, by the way, the primordial thing. And if you do have a satellite which is launched, it could detect this gravitational waves from the early universe. Now, this is very different from the gravitational waves you're seeing in LIGO. These are from nearby universe, and also these are classical waves. These gravitational waves have quantum origin, and that would be something remarkable. If you hear the Nobel Prize lectures of Ray Weiss and Kip Thorne, who got the Nobel Prize for gravitational wave, they both said that this is the next big thing that would happen in science. So we hope that someday, we are talking to ISRO, and maybe ISRO, NASA, ESA, we'll all get together to do this. Okay, I'll stop here and tell you that we are just beginning cosmology. We have an idea of what a uniform cosmology would look like, but as someone pointed out, we don't know what happened at Big Bang. So at those times, maybe the whole space-time is like a foam, right? And there's some messy thing. I don't know whether we will ever know about it, or perhaps we will be smart enough to have ability to detect signatures of that. So that's for you guys. Thank you.
So we have time for a few questions, and it was very interactive, but you can catch them also on campus.
Yeah, so, okay. No off topic. First on topic questions. On topic questions. Are you on topic? Okay.
The universe is expanding, so that means the cosmic background radiation is also expanding? So it shifted into the microwave spectrum?
So I showed you this curve, up and down curve. It will change a bit in 100 years.
So
but
at
the
some
level
point,
of 1 part in 10 to the 7. Okay, it's the shift. So we are just assuming we will be smart enough to have detectors which will see this.
at some point in the past, was it all visible? Because it would have been in the visible light spectrum if it was expanding. Was it all, we could
So
see the radiation?
If you went to that plasma surface, it's glowing like the surface of the sun.
Right.
It's as hot as the sun. I mean, a little less hot, but yeah, it's like the surface of the sun.
You mentioned that light is the fastest thing in the universe.
Sorry?
So light is the fastest thing in the universe. So is the growth of the the expansion of the universe faster than that?
I mean, if you again go to this velocity interpretation, certainly possible. There's no limit on how fast the universe can expand.
So it's not really clear.
Which also is the reason you have this space. You have this warp drive in Star Trek that actually is in principle possible. Okay, but practically, you need to do that. That's because you can do things with space which are not constrained. Okay. Oh, yeah.
Yeah. So because the universe is expanding, I just have a question if there can be chances of having a multiverse, like multiple universes, like how we have multiple galaxies.
Yes, so I showed you that a lot of possibilities exist in the very beginning. Okay, so there could be another bubble, another universe somewhere. But the point is, it almost is metaphysics because we have very little chance of seeing anything from another independent universe. So it's a bit of just philosophical thinking. Okay, yeah.
Sir. Good afternoon, sir. Sir, here.
Is anyone?
Sir, I'm standing here in the corner here. Sir, at the back, last row.
Oh,
here.
okay, okay.
Yes, sir. Sir, I had questions just slightly unrelated, but still I think not exactly on topic, but I want to ask you first, I had read somewhere that essentially the magnetic poles switch Every
No,
300.
that's totally outside the realm of cosmology. What, Earth's magnetic pole switching?
Yes, sir.
Yeah, so I'm not an expert on this. The closest person I can think of is Deepankar Bhattacharya, who works on magnetic fields of pulsars, but he knows a lot of things, so he may be able to explain this. I know what you know, so I know that people have measuring things. So let's keep that to that.
My question is that you told that our universe is constantly expanding, but if we see relativity, then planets, so object having higher mass pulls an object having lower mass. So why the universe is expanding? It should contract, right?
Yeah, so that's a very good question. With all the matter density, why does the universe expand? So that has to do with the initial expansion that started. So if the matter density was much larger than what we have measured it to be, the model would have predicted that the universe will recollapse, and that was called a big crunch. So you had a big bang from where it starts, and then there's a big crunch. But it so happens that we seem to have inferred a universe which will expand forever and at an ever increasing rate, and so much so that slowly distant galaxies will get out of our view, and we'll be a lonely little, only our local galaxies which are somewhat bound to us will be visible. But that's billions of years in the future, so don't worry about it.
Hello, sir. I have a question. Sir, I want to ask, what is your point of view on life outside Earth, and do you believe in aliens? Thank you.
My view on that is not a, expert view. It's like anyone else, but probabilistically, I find it very difficult to believe that you won't have life anywhere in the universe, just given the number of sites for that. Now, how difficult was life to originate on Earth is something that biologists and various people have to tell us. So what we are doing now is looking for chemical signatures in the exoplanets. That's what James Webb's biggest thing is. It's looking for chemical signatures of life in distant planets, in the atmosphere of, like if you look at Earth from a distance, there will be chemical signatures of us being there, or any kind of, largely the planktons being there. Okay.